Hello, welcome to Build Succeeded. Time to shed some light on this engine. Literally. My name is Lucian and today I'm going to implement lights in my 3D engine. If you haven't seen the first episodes of the series, I suggest you go back and watch them. We're going to continue from where we left last time. Links in the description of the video. We're going to implement three types of light in this engine: ambient light, directional light, and point light. Let's take them one by one. Ambient light is the type of light that bounces off so many surfaces it doesn't have a specific source or direction anymore. It's similar to the light you see in a room on a cloudy day. It doesn't really generate shadows and it's just there. This is what we have so far, a texture rotating cube. No light is taken into consideration at this point, but we're going to change that. I'm going to add support for my lights. I'll start with a union called color union. In C++, a union is kind of like a structure, but with all variables sharing the same memory. In my case, the integer called color, which is 4 bytes long, will share the same memory with the color item structure, which contains 4 unsigned chars, 1 byte long each. How does this help? In Direct2D, a color is represented by an integer, with each of its bytes representing the level of the three base colors: red, green, blue, and alpha. This helps me quickly convert a color to its RGB parts to manipulate them easily. Now I need to add a light class. This class will hold the details about each light in the game, like position, direction, color of the light, and the type. Initially, for ambient light, the position and direction are not relevant, but they will help us later with the other type of lights. To add support for lights in the engine, I'll update engine base with a vector of lights called lights and a couple of methods to add or remove lights from that vector. The triangle class needs some changes too. This is where we calculate how the light will affect the displayed color. So I'm going to have a variable called light amount, which will start as 0 and as we apply lights can increase to a max of 255 for each colored byte. Now I'll add a method called applyLight that receives a light and tries to update light amount based on what we receive. First we calculate how much light we can add before reaching the maximum. Then calculate % to apply. This will always be 1 or 100% for ambient light, but it will change for the other types of light. Finally, we add to the light amount based on the light source and light to add calculated earlier. I'll also update the constructor to receive the light amount, so we don't lose this information when we clip the triangles. Then reset the light amount after calculating world points. Finally, when drawing each pixel of the triangle, we now need to calculate the color of the pixel by applying the amount of light to the texture color. Now in the engine base class draw method, before we calculate the camera view for each triangle, we call applyLight for each light in the engine. Let's initialize and add an ambient light to the engine and run the application. There is no difference yet, but if I decrease the amount of the light from 255 to 32, look what happens. The cube is now barely visible, being in weak light. Now if I change the amount of red to 255 and the green and blue to 0, we're going to see the cube having a red tone. The next type of light we're going to implement is directional. This type of light is similar to the light of a shining sun. The light rays are all almost parallel, so in our ideal environment, this light does not have a position, but it does have a direction, represented by a 3D angle. This is where it gets a bit trickier, because now we have to calculate how much light falls on each surface based on how the surface is facing the light source. A light that falls from an angle on the surface will light it less. To make this possible, first we'll have to calculate each triangle's normal vector. The normal vector is the 3D direction that falls perpendicular to the triangle surface. And we can calculate it using this mathematical formula. After calculating the normal, we will use the dot product between the normal and the direction of the light to verify how aligned the two vectors are. Dot product uses this formula here and returns a number that can be negative or positive. If negative, the two vectors are facing different directions. If positive, the two vectors are facing the same direction. Let's implement the two methods in engine base class. This is calculate normal. The best way to work with vectors in this situation is when they are normalized, so we'll do that first. Normalization means changing the vector's components in 3D in such a way that the length of the vector becomes 1. After normalizing the two triangle vectors, I just calculate the normal using the formula. The normal calculated based on two normalized vectors is also normalized. And the calculate dot product method uses the simple mathematical formula to calculate the dot product. If both vectors are normalized, this will return a number between -1 and 1. Now I'll add a point 3D to the triangle class to represent the normal and calculate it right after world points. To use it and apply the second type of light, we'll go to the apply light method and calculate percent to apply using the dot product. I'll just make sure to not go negative with it. Due to the normalization we did, this will always be between 0 and 1. To see the results, in the engine class, I'll dim the ambient light to 31 out of 255 and create a directional light along the z-axis. If I run the application, it looks like the cube is lit from our direction. Let me move to the side of the cube. As the cube turns around, its surfaces are lit or dark depending on the rotation. The last type of light I want to implement is a point light. This is similar to a light bulb in a room. The light has a position, but it doesn't have a specific direction. That means we can use the same principle as for the directional light, but this time we need to calculate direction for each triangle, depending on its position. The main class where we have to work here is the triangle. If the light type is a point light, we need to calculate the direction as the 3D vector difference between the center of the triangle and the light's position. Then, after normalizing the direction vector, we calculate percent to apply the same way as for the directional light. Let's remove this directional light from the engine class and add a new point light right in the middle of the world. If we run the application now, there is no big difference. It looks similar to the directional one. To see the difference, I've added the second cube and put the light right between them. Now you can see that each cube is lit on the inside. This is point light. In order to make a point light dim with distance, I'll add another variable on the light class called distance, representing the maximum distance this light will travel. Then in the triangle class, I compare the light maximum distance with the distance to the triangle. Then I calculate dim as a percentage based on the distance and use that one to dim the percent to apply variable. This is it. I'll leave you with this scene of two cubes lit with different lights from different directions. Thank you for watching this episode. In the next episode we're going to load Blender models and implement Z-buffer. Give me a thumbs up if you like this video and subscribe to be notified when my next videos are up. See you soon.